This is great pleasure to have Professor Young-Wook Lee as today's speaker. My name is Young-Wook Bang, the president of APCTP. As a president, recently I realized that cosmology and astrophysics is going to be the most exciting and challenging subject or field in 21st century for fundamental physics. So our center decided to extend and stimulate this growing field, astrophysics and cosmology, so that we are organizing a series of lectures, mostly organized by Dr. Colgáin and Appleby of our center's the research of our center. And if you visit our website, this series of lecture named as Dark Energy in Dark Age have already recruited exciting list of speakers. For example, last 2 weeks ago, already Dr. Eric Linde gave an exciting talk. Then also Misao Sasaki gave a series of talks in two weeks ago, I think. And I was also told that in next month, Kulum Bapa will give talk in our program. Today, anyway, the Professor Young-Wook Lee is going to give very stimulating talk, I would say so, because some months ago, he reported very controversial claim with his paper. So today, I think he will give us more details talk about his claim. So let's welcome Professor Lee. Okay, welcome.
Thank you. So may I start now? I guess, yes. Okay, I thank the director, president, and organizers for inviting me to this lecture series. It's my great honor. Today, I'd like to share with you our interesting progress in investigating luminosity evolution in supernova cosmology. In particular, I'd like to show you and perhaps convince you that the key assumption made in the discovery of dark energy is in serious error. And the discovery was made in supernova cosmology. So I will only talk about supernova cosmology. The name of our project is Yonsei, after our host institution. Yonsei stands for the Yonsei Nearby Supernovae Evolution Investigation. And we started this project 10 years ago. For this project, the Lee Kang, who was my student, and now the postdoc at Gemini Observatory, was responsible for the spectroscopy of host galaxies. And you must remember that we are doing this project in a country without telescope. Until recently, the Korea had no telescope time at the research grade telescope. So even with the money, it is very difficult to getting the telescope time in Chile and Arizona. So you must understand that our situation is very, very different from physics, chemistry, and biology. And Young-No Kim, who was also my student now at France, Lyon, was responsible for the crucial light curve analysis, the standardization of supernovae 1A. Only 20 people or so in the astronomical community worldwide know what is going on in the standardization. So he's one of them. And Chul Chang, who is a research professor, is doing many things, including the age dating, the population synthesis models, the Yonsei model we call YEPS, Y-E-P-S, and also statistical analysis. And Professor Young-Wook Lee, one of our faculty members, is helping us in the statistical analysis. And Dong-Wook Lim, who was also my student now at the Heidelberg, and Chang-Hee Lee at CASI, they were involved in the early part of this project for the spectroscopy and photometric analysis. Okay, the most direct and perhaps the strongest evidence for the accelerating universe with dark energy is still from supernova cosmology. I'd like to remind you that what they found is that a supernovae at high redshift are fainter by only 0.2 Mach. That's 20% in terms of brightness. So compared to the model without dark energy. So after the empirical standardization, this is an important point. After the empirical standardization. So because they are fainter at high redshift, but it was interpreted as evidence that they are farther away in cosmological distance, which was most naturally explained by the accelerating universe with dark energy. But I'd like to emphasize that an alternative interpretation is also possible. And as you all know, the stellar populations in host galaxies are getting younger with redshift. So it is possible that supernovae at high redshift are fainter, not because of dark energy, but because the stellar populations are younger, and their progenitors are younger, and therefore more massive compared to their counterpart at local universe. This is entirely possible, and this has to be tested. Okay, this is supernova progenitor age distribution, SPAD. The SPAD can be calculated by converting these two functions, delay time distribution of supernova 1A, that is the characteristic time after the star formation until the explosion of type 1A supernova. And this is the cosmic star formation history, which is very well known from the observations. So by converting these two, we can calculate the supernova progenitor age distribution as a function of redshift. And as you can see that we expect both old progenitor and young progenitors at local universe. However, we, of course, would observe only young progenitors at high redshift. So from these diagrams, we can calculate the luminosity evolution, redshift evolution of median supernova progenitor age. Well, according to that, it is about 6 gigayears, 6 billion years at local universe, and declines to about 1 gigayear after redshift of 1. So we have about 5 gigayear difference in progenitor age between redshift 1 and redshift 0. So there is a significant difference in stellar population age between local and high redshift. Okay, the history tells us that we should be concerned about this. We should be worried about this because since 1944, this is a famous story in astronomy. Walter Baade realized that the population 1 Cepheid variable stars, which is younger and more massive, are brighter than population 2 counterpart, which is older and less massive. And of course, and Hubble did not realize this because at his time, they had no concept of stellar populations. And therefore, Hubble made a critical mistake in measuring the distance to M31, the Andromeda galaxy. And he observed population 1 Cepheid in the disk of Andromeda galaxy, but instead applied the period luminosity relationship of population 2 discovered by Shafieloo, mostly from globular clusters. So because of Baade's discovery of Hubble's mistake, the M31 distance has been increased by a factor of 2, and the H0, the Hubble constant, has been decreased by a factor of 2. So this incident already illustrates that the luminosity of standard candle can depend on stellar population age because the mass is different. This kind of problem still continues in today's astronomy. We have another debate going on in the Milky Way bulge, but exactly the agenda is whether it is distance or whether it is stellar population difference. So this problem still continues in today's astronomy. And another more relevant history is the Tinsley-Sandage debate in 60s and 70s. At this time, the Allen Sandage was dictating the observational cosmology. He was using the integrated luminosity of giant elliptical galaxies as standard candles. At that time, they had no idea about the supernovae. So the brightest one was the giant elliptical galaxies. But he was using, but as correctly pointed out by Beatrice Tinsley, then the graduate student at the University of Texas. Later, she became the associate professor at Yale University, but she discovered this problem while she was a graduate student. And she correctly pointed out that the luminosity evolution was underestimated, somehow underestimated by Sandage, and therefore the distance was underestimated, and incorrect cosmology was proposed. I think these mistakes by Hubble and Sandage led to this famous quotation from Rondo. Probably some of you are already aware of this. I'm an astronomer, but I cannot agree more with this. Not only astronomers, but also physicists. We all make mistakes. And this is the reason why we should make every effort in investigating the possibility of an alternative interpretation in each cosmological observation. This should be encouraged in the community and should not be discouraged, even after the WMAP and Planck GMB observation. I'm especially concerned on the supernova magnitude standardization. Type 1a supernovae are not standard candle. You must remember this. But they are standardizable candle. Because before the standardization, the luminosity of supernova 1a varies by more than 1 magnitude. So that's about almost 200% in terms of brightness. So without standardization, we cannot use them as a standard candle. And the standardization procedure is very, very empirical procedure. What they do is they stretch the right curve or they squeeze the right curves. So all the right curves can match each other at some midpoint here, at the middle point. An additional correction is made based on the color, which has something to do with the temperature and interstellar leavening, dust leavening in the host galaxy. And important part is, and then they assume that this procedure does not evolve with redshift. So this is the key assumption made in the supernova cosmology. I'm not sure whether we can do that. I'm very uncomfortable with this procedure because this is not like the period luminosity relationship of Cepheid. They don't stretch, they don't squeeze in the case of Cepheid variable. They simply use the observables directly, the period and luminosity. But in this case, they add some manipulation, which is not confirmed from theory. It's just purely empirical ground, they stretch and So I'm very much concerned on this. In practice, the standardization is very complicated procedure. As I said, only very few people understand exactly what's going on in the standardization procedure. But the bottom line is that in the SALT 2 light curve fitting, which is the most widely used technique for the standardization, the MB, which is the absolute magnitude, after standardization, and the alpha parameter has something to do with the light curve shape, and the beta parameter has something to do with the color. They are all fitted at the same time as cosmology. And this means that both old and young progenitors were used in standardization. But as you know, only young progenitors are observed at high redshift. So this could introduce some systematic bias, and they can introduce an overcorrection, for example, or undercorrection in standardization for younger progenitors at high redshift. We cannot rule out this possibility, for example. So, of course, they were aware of this potential problem in standardization. So what was the evidence they used to convince themselves and others that the luminosity evolution is negligible? The early investigators, including Schmidt, Rees, and Perlmutter, all recognized that the key assumption, which is no luminosity evolution in supernova cosmology, can be best tested at local universe by looking for any correlation between the population age of host galaxy and the Hubble residual of supernovae. And since measuring population age is not that simple at that time, especially, they used the galaxy morphology instead as a proxy for population age. And they found no difference in Hubble residual, which is proportional to the supernovae absolute magnitude after standardization, between early type, which is relatively older, and late type galaxies, which is relatively younger. Therefore, they concluded that the luminosity evolution is negligible. However, more recent and larger CFA dataset show different result. They found the difference is 0.14 magnitude between old and young host galaxies. 0.14 magnitude this is not trivial difference, because if you remember, the magnitude difference used to input the dark energy was only 0.2 mag. So this is a significant fraction of that. However, this was 2009, after the WMAP result for the CMB, and simply this result did not get any attention from the community. I think this is just not fair. This is not fair, because the CMB cannot be and should not be used to argue that there is no luminosity evolution in supernova cosmology. CMB, as you know, has something to do with the early cosmos. Supernova cosmology is relatively late history, and they totally have different physics. So we should not connect that like that. There are other well-established correlations from host galaxy studies. It is now well known that the supernovae 1A in the less massive host galaxies are fainter by 0.1 mag. And also, supernovae 1A in locally star-forming environment are about 0.16 magnitude fainter than those in passive environment. Since the mass of a host galaxy cannot tell the supernova in that galaxy to be bright or faint, this is most likely due to the population age impact. However,
sorry, could this just be down to dust?
Excuse me?
Could this number 2 just be down to dust? What could it be down to? I mean, physically.
I did not catch your point.
Can you explain it just in terms of dust? Like, we really don't know much about dust.
Dust?
Yeah. I mean, does it affect all the bands as well?
Yeah, there was a recent suggestion that dust could be a origin for this well-known mass correlation. But also very recently, 2 papers with infrared observations report that the dust cannot be the origin for this mass correlation. So,
and because we see things in different bands, like it probably, I mean, if it was dust, it would affect different bands.
yeah, so these 2 papers by, one of that is by Pondo et al. It just published like several weeks ago. And the other paper by Udin et al. They all used infrared photometry and concluded that the dust cannot be the origin for this the mass and Hubble residual correlation. So you can take a look at it. These 2 papers just appeared in the Astro PH. But what the supernova community is simply making an additional empirical correction based on host mass, regardless of redshift. And frankly speaking, this is the most strange correction that I ever seen in astronomical research. It has been 31 years since I received my PhD. And this is the most strange correction that I ever seen. And because the redshift evolution of host mass is small for the redshift range relevant to supernova cosmology, this correction has negligible impact on cosmology. Instead, what is needed here is that this has to be converted to age effect, and then the correction should be a strong function of redshift. So in order to do that, we need information on age. So in order to directly test the age effect, 10 years ago, in a country without telescope, we initiated the Yonsei project. So for which we have obtained very high quality spectra for most of the nearby early type host galaxies reported in the literature. They are nearby but distant enough to be on the Hubble floor. We use only early type galaxies because high precision age dating is possible, and also because extinction is negligible in most cases. So for the first time, we are directly measuring population age and metallicity from spectral absorption lines such as H-beta and ion lines, and together with well-established population synthesis models from 3 different groups, including our own Yonsei model. And we use the SALT2 implemented in Solana package for the right curve analysis and standardization. This was done by Young-Wook Kim. So I'd like to emphasize that this is the most direct and stringent test ever made for the luminosity evolution. So this is an example of our host galaxy spectra, where we can clearly see the difference in the strength of H-beta line between a young and old host galaxies. And this is mainly because the temperature of stars in the main sequence are getting cooler with increasing age. By comparing our high quality spectra with 3 different population synthesis models, including our own, we can measure population ages and metallicities simultaneously. Again, this is very well established technique in early type galaxy community. Unfortunately, we cannot use all the data we obtained because some early type galaxies, although morphologically classified as early type galaxies, show signs of dust, signs of recent star formation, such as emission lines and the infrared excess and such. So if that is the case, that the derived ages can be very seriously underestimated or highly uncertain. So we had to carefully remove these non-genuine early type galaxies. So after removing these non-genuine early type galaxies, out of 59 that we observed, only 34 galaxies were used in the final analysis. Nevertheless, we found an important correlation between population age and Hubble residual, in the sense that the supernovae in younger environments are fainter after standardization compared to their older counterpart. If there is no luminosity evolution, and if standardization is perfect, then this should be a scatter diagram. But we can clearly see the correlation. Well, I admit, because of relatively small sample size, it's not 4 sigma result. But still is close to 3 sigma correlation. So we admit that this should be confirmed with a larger sample. We also found a very tight correlation between postmass and population age. And this is significant at 99.99 point confidence level. So this is more than 4 sigma correlation. But we found no correlation with metallicity. So the well-established correlation between host mass and supernova luminosity should be due to population age difference. So this is another important result. This is not very well known, but this is equally important result we obtained from our spectroscopy. And as already showed, supernova progenitors in host galaxies are getting younger with the redshift. About 5 gigayear difference between redshift 1 and local universe. So our result inevitably indicate a serious systematic bias with redshift in supernova cosmology. This is just to illustrate the significance of the luminosity evolution. So let's go back to the discovery time, the 1998, 22 years ago. So the Hubble residual is calculated with respect to this cosmological model without dark energy, as has been done by Adam Lees and others in their discovery papers. And the red line here is the evolution curve based on our age dating, our result between population age and Hubble residual, and assuming this model, the model without dark energy. And the black curve is the lambda CDM model with dark energy, the concordance model. We can clearly see that the luminosity evolution is mimicking Hubble residuals used in the inference and discovery of dark energy. After our result has been published in January, in some media report, Adam Lees and other people expressed their concerns, criticism, and they argued that our result is based on a small sample of early type galaxies, and therefore correlation is not that strong. Well, we admit part of this because we wanted to observe more sample, but simply there is no enough nearby early type host galaxies in the universe. So although we observed all of them with very high signal to noise ratio. So they can say that, But in addition, Adam Lees in particular pointed out that our slope is not confirmed from a large sample of host galaxies comprising all morphological types. And he showed this diagram in that report. Now this is an important point because early type galaxies are minority among the supernova host galaxies. they constitute only 25%. The other 75% is ray-type galaxies. But our result, because of the age dating and dust extinction, we need to limit our sample to early-type galaxies. So they were wondering whether our result from early-type galaxy can be extended to all morphological types. So they can argue that. So this is something new. So we need to pay attention to this. And in the recent APJ letter paper just published, the same diagram was used by these authors, Ben Rose, Adam Rees, and their collaborators. And they claim that our age Hubble residual slope obtained from early type galaxies is not compound from the age data set measured from multiband optical photometry of host galaxies comprising all morphological types. So they argued that, therefore, that there is no evidence for luminosity evolution. Well, photometric ages are generally very uncertain. And that's the reason why we measure the spectroscopic ages with high signal to noise ratio. But this particular data set by Rose et al. Is more reliable, based on more reliable photometric age dating technique for the mass weighted ages. So we need to take care of this data set. But as you see here, somehow they only presented this probability density plot without showing individual data points. So we were very curious. So of course, here we have plotted the individual data point. And guess what? We found a surprising reversal from their data set, comprising host galaxies of all morphological types. When you apply the regression analysis with the standard MC-MC posterior sampling method, very significant 4.3 sigma correlation is obtained between population age and Hubble residual, both for the global age and local age near the site of supernova in a host galaxy. With the slope, highly consistent in excellent agreement with our previous result from spectroscopy of early type galaxies. Although the associated error bar here is larger than that of our spectroscopic age, the sample size instead is much larger with 102 host galaxies compared to 34. So therefore more significant statistical result is obtained from this data set. Then why did they say different conclusion? So we found that the original analysis of Rose and Rees et al. Is highly affected by regression dilution bias, therefore severely underestimating both the slope and significance of the correlation. As I said, they only presented this probability density map without showing the original individual data point. Their density map is based on a Monte Carlo resampling method of generating 100 random mock samples around each real data point according to the measurement error. I don't know why, but they did this. In doing so, however, the age range has been stretched. So slope has been underestimated, seriously, severely underestimated. And in statistics, this is the well-known regression dilution bias. And that arises because of a measurement error in the independent variable. So in the Rose and Rees analysis, the dilution bias has been doubled because in this diagram, because of the measurement error, the ordinary the risk fitting has been diluted compared to the best fit already. And because of the random mock sampling, the slope has been diluted further. And unlike the original the regression line of the Rose and Residual, the best fits obtained from the same standard MCMC posterior regression analysis for both Rosidual sample and our previous sample, they show excellent agreement. So this cannot be a coincidence. So if properly done without dilution bias, even the data set originally used by Rees and Rose to argue against our claim is instead strongly supporting our result from elliptical early type host galaxy, even more so than our previous result. In addition, this new data set is shows more significant 4.3 sigma correlation between population and Hubble residual from a larger sample size. So this should be compared to our roughly 3 sigma correlation. And also, this provide, unlike our previous result, this result is no longer limited to early type galaxies, but because they are based on host galaxies of all morphological types. So we can apply this result to the all supernova host galaxies. And also, unlike our previous result, in the cosmological application, no extrapolation in age is required below 3 billion years because the Rosidual sample contains younger host galaxies, as young as 1 billion years. So we can apply this result to the high redshift without extrapolation. We had to use some extrapolation in our original investigation. And also, in addition to the global population age, this study provides the local population age near the site of supernova, which is more relevant to the supernova progenitor age. And from the local age, we obtained even steeper slope. So luminosity evolution stands up to scrutiny as a serious systematic bias in supernova cosmology. So again, here with the steeper slope we obtained from the local age, the delta Hubble residual over delta age, with this slope together with the redshift evolution of the median supernova progenitor age that we showed you before. This is the red line is again the evolution curve based on this model without dark energy. And you can see that the fit is now better than before, fully mimicking Hubble residuals used in the discovery and inference of dark energy from supernova cosmology.
But I guess we now have a lot more data points for supernovae, right? So
this data is just binned data. This is from 10,000 supernova, all the observed. This is from the union sample, the B2 So this supernova data is just binned data. So you don't need to worry about.
Okay, that's fine.
And the gray shading is 1 sigma significance interval added to our evolution curve. So we have submitted this paper and already received the report. So we are working for the revision. Well, it's not that easy as you can guess, because all the judges are affected by the religion called dark energy. So, however, sooner or later, I think this will be published without problem in APCTP letter. We are working on it. Okay, so we have plenty of time, but I need to conclude. So conclusion. So supernova cosmology is based on such a fragile assumption, which is not supported by direct age dating of stellar populations in host galaxies, and the age Hubble residual correlation derived from those observations. Even the data set originally used by Rees and Rose to oppose our claim is now strongly supporting our conclusion, even more so than our previous result. Taken at face values, the luminosity evolution appears to be significant enough to question the very inference of dark energy from supernova cosmology. So how this result from supernovae can be accommodated with other cosmological studies, such as CMB and BAO? I don't know, but this would be an interesting and important avenue, direction of the future studies. And I hope that and I'm sure that many of you can do that in the near future. At the same time, since the supernova cosmology has long been considered as the first and the most direct evidence for the accelerating universe with dark energy, our finding may call for some equally careful investigations for the possibility of an alternative interpretation in other cosmological studies as well. Well, now I'm old enough, approaching 60, to know that we all repeat the same mistake. In astronomy, intrinsically fainter or brighter population stars is often misinterpreted as a distance effect by many investigators, including Hubble and Standish. So by now, as of today, I'm pretty convinced that the so-called discovery of dark energy from supernova cosmology in 1998, 22 years ago, I think that was nothing but yet another case of this repeated mistake. I'm embarrassed and frankly speaking, very sad to know this personally, that this can happen. So in any case, as always,
JD's here complaining he hasn't got the Nobel Prize yet, and Adam Rees has got. There you go.
I'm not interested in that prize.
Well, you wouldn't want it now. Adam's got it.
So in any case, as always, as you would agree, we should be open-minded to any possibility to come. We are scientists, after all. That's all? That's all?
Without acceleration, you need to have the smaller concept.
I cannot hear you.
Yeah, hello.
Hello.
Do you hear? So, without acceleration, we don't need to...
I cannot hear you. Please someone relay that message.
Yeah, mask. Okay. Yeah, keep your mask on. So, without acceleration, maybe we don't need small cosmological constant directly. It is better in theory, actually, to have very small cosmological constant, 10 to the minus 3 electron volts to the 4. This is cumbersome in a sense. So string theorists will like that.
Yes, string theory certainly will like this, right? So just to put this in context, so string theory seems to have a problem embedding lambda. So finding a vacuum that corresponds to lambda. So they will certainly like it. Actually, let me make one comment. We did some work recently on a quasar. You're still there, yeah? Hello?
Hello.
Yeah, so we did some work on, so recently and Luso have a quasar data set. And basically, if you fit it to flat lambda CDM, you find you're within 1 sigma of a universe with no dark energy. And this in some sense is a sympathetic data set for what you're saying.
No, I have to take a look at that first. But
they don't,
I'm an astronomer and just starting observational cosmology. My specialty is stellar evolution and stellar population. So what we do is we measure ages of stellar population, and we simply apply that to the supernova cosmology. So our knowledge on other part of the cosmology is rather limited. And I'm not going to do that because I have to do this for a long time. So we will take care of this part. So you take care of your part. Okay. And then we'll see.
So I meant to be chairing this. So are there any questions, comments? Ginny has another question.
How will it change the 6-parameter fit of Planck data? Without lambda CDM, how will it change the analysis of Planck data?
Well, again, I'm not specialist for the CMB, and I saw that the Di Valentino, she will talk about the CMB in 2 weeks or so, in maybe 3 weeks. So I'm looking forward to hear her result. And if I remember correctly, they found some discordance with LCDM from recent Planck observations. So we are not alone in that sense. In CMB, they are challenging in some part on the concordance model.
Any more questions? People online? Nope. And it seems like we've no questions here in the seminar room. So I would like to thank you very much for a very entertaining presentation.
Thank you.